All right, so the first Gauss's law super example, I like to call them because it's three examples of charge distributions that we can calculate the electric field from, and I call them super examples because really just about every time we use Gauss's law is related to one of these three examples. So if you know these, you're pretty good as far as Gauss's law goes. And if you look at the objectives here on the screen under 3B, students should understand Gauss's law so they can. Under number 2, it says apply the law along with symmetry arguments to determine the electric field for a planar, spherical, or cylindrically symmetric charge distribution. And those are the three super examples. The one that we're going to look today is the first one, the planar charge distribution. So let's get started. All right, so the idea is we've got an infinite plane of charge, right? There's positive charge spread out uniformly over it, and we want to find the electric field that comes about near this plane using Gauss's law. So what we've got is a surface charge density of sigma, and what I mean by surface charge density is how many coulombs of charge per area on the plane there is. Right? We can't just look at the total charge, because if we have an infinite plane and we spread charge out over an infinite plane, we're going to have an infinite amount of charge, right? But what we can talk about is how much charge there is per unit area, right? So that's what we're talking about here with this sigma, this charge density. Can anybody tell me what units sigma would have to have if we're talking about a charge per area?
Meters got to be in.
Say that again?
Has to be at least meters in there, meter squared.
Does have to be a meter squared in there, right? Because we're talking about how much charge per area. But what other unit would need to be in there if would need to be in there? Charge per area. That's what the surface charge density is. So the units would be, well, what's the unit for charge?
Coulombs.
Coulombs. And the charge, and the unit for area, like we said, is meters squared. So the units for sigma charge density is just coulombs per meter squared, right? So how many coulombs is in 1 square meter of this infinite plane? All right, are we pretty clear on what we mean by surface charge density? How many coulombs per square meter are on our plane? All right. So now, when we use Gauss's law, right, and this is like written out Gauss's law here, the surface integral of the electric field dot dA is just equal to the charge enclosed in the surface divided by the constant, epsilon naught. Right. So, and what we're trying to do is use this equation to find E, right? We want to solve for the electric field, and we can build or construct what we call a Gaussian surface. If we can if we can be smart about what's about a surface that we can pick, that we can make this integral easy to do, then we can find the electric field. Right? So, how do we know when we can use Gauss's law? How do we know we can make this, generally very difficult integral? How do we know we can make it easy to do? A good way to think about it in the textbook, Survey and Jewett give you a good few rules of thumb that will show us when we have a symmetric enough situation that we can use Gauss's law. So I'd like you to take a look at these rules here, and this is in section 24.3, which I'd like to make sure you study tonight because it's got all 3 of the Gauss's law super examples in it. But that integral, the surface integral of E dot dA, is going to be possible to do or to simplify if we can meet one of these 4 conditions. So either we can argue that over the portion of the surface, the electric field, we know it has to be constant, and we might be able to say that by symmetry considerations. And I'll talk a little bit more about that in a moment. And if the electric field we know is constant over the surface, then we can pull the electric field out of the integral, and then we can do the integral, because if it's just an integral over the area, we're going to end up with the area. The second possibility is that the dot product, if the electric field and the area are parallel over part of that surface, we know that E dot dA is just going to be the magnitude E times the magnitude dA, which is going to be an easier integral to do. Or maybe we know that the electric field is perpendicular to the surface, and we can just say it's 0, right? In which case, we don't need to do the integral because we know it's going to be 0. And then, of course, number 4 there says if the electric field is 0 over a portion of the surface, well, if the electric field is 0, the integral of the electric field times the area is going to be 0 as well. So if we have a situation that's symmetric enough to meet one of these conditions, then we can use Gauss's law to find the electric field. All right, so going back to the paper here, let's get started. So I've got a pretty badly drawn, 3D picture of an infinite plane of charge here. And I'm gonna make a Gaussian surface, or I'm gonna construct a surface here that we can figure out what the electric field is over a couple parts of it pretty easily, and then the other one's gonna simplify down to a easy to do integral. So I'm gonna draw a cylindrical surface. All right, so one end of the cylinder is gonna be on this side of the Gaussian surface, and I hope I can draw this so that it looks all right. And then the other half of the cylinder, and the cylinder kind of passes through the Gaussian surface. So the other half of the cylinder is behind the surface the way I'm drawing it. All right, so think of a cylinder passing through the surface, passing through the plane of charge. We can see this half of the cylinder because we're on this side of the plane. We can't see the other half because it's behind. Right. So this is the surface that we want to figure out what is the flux through, right? Because if we know the flux has to be proportional to the charge that's inside of it. All right. And why don't I quickly show the it's basically this picture here, right? You've got this is part of the infinite plane of charge. You can see the Gaussian surface here, right? It's a cylinder.
So don't we have to calculate the area that the cylinder is taking?
Yeah, we will. So right. So really, if you think about it, this surface has our Gaussian surface has three parts to it, right? There's this circular piece on this end. There's this circular piece on the other end, and then there's the curved, cylindrical portion of it, right? So we're gonna look at each of those three surfaces individually, and see if we can figure out what to do with each of them. So the first thing we need to say is, is there any symmetry in this situation that can help us? Let's start by figuring out maybe if we can tell what direction the electric field has to be. If I'm on this side of the surface, I've got it's infinitely big. Can I say what direction the electric field has to be near this near this charge? What direction do we think the electric field is going to be? And we can be pretty certain just by thinking about the symmetry that's in the situation.
It's going to be pushing away.
Yeah, it's going to be away, right? And it's got to be coming perpendicular to the surface. It's got to be pointing directly out, right? It's got to be pointing directly out from the surface. Let me draw it so that we can see that that's perpendicular. Hard to do on a 2D piece of paper. But we can be positive that the electric field is pointing outwards from the surface. And the reason that is, if it's pointing in any other direction, right? If it was pointing, kind of at some angle, then if you rotate the surface, you would change the direction of the electric field, but we'd still have the same infinitely charged plane. So if we rotate it, we would expect the electric field not to change at all, right? And symmetry considerations are used all the time in physics, right? We can It's very powerful. Like we can use, we can determine a lot of things just by saying, well, this plane of charge is symmetric. So if we rotate it, we can't have a different electric field if we rotate it because we have the same infinite plane of charge. So if you kind of follow that line of reasoning, we can see that the electric field, if there is one, I guess, would have to have a direction of out of the plane of charge. Right? If it's negative charge, it would be into. But the point is, from symmetry, we can tell it's perpendicular. So that's going to help us figure out, in Gauss's law, we can find the flux through the, let me call this part, if I call this end cap part 1, I'll call the cylinder, the round cylinder part 2, and then the other end cap we'll call part 3. Let's look at part 2 first. Maybe I didn't number those the best. But if we look at the round part, what's the flux passing through this part of the surface, the curved part of the surface?
Zero.
Zero. Exactly. And can you explain why?
Because it is parallel to.
Yeah. That's right. Well, yeah, the electric field is parallel to the surface, right? Since the E field is pointing directly outwards from the plane of charge, none of it passes through this rounded cylindrical portion of the surface because that's parallel. So that makes things a little bit easier. We know the flux through that part of the surface is just 0. Right? What about this part here?
Would be.
Go ahead.
Wouldn't it be the electric field times the area?
Yeah, exactly. We know that the electric field here is well, let's see. Right, we're always starting with the integral, right? The integral of E dot dA here. We know that the electric field here is always going to be perpendicular to this surface, right? So the normal to the surface is also directly outwards from the plane of charge. So this dot product, this is one of those cases where this just turns into an EdA, right? Magnitude. Right, and that's because here, E dot dA, right, what I mean to write is E is, yeah, that's all I mean, is that E dot dA is just in this case going to be equal to EdA because the electric field is pointing directly outwards from the plane of charge, and so is the dA vector. Right. So that means our integral, we can take the electric field. Whoops. I want to see if I can explain why we can take the electric field right out here without. Because the answer that we're coming up is that the electric field is going to be uniform, but I don't want to pull that out. Yeah, 1 second here. Well, yeah. So anyway, let's go and say that in this case we have a flat, right? This piece of the surface is flat, so the electric field in this piece is just going to be, this integral is just going to end up being E times the area, right? Because the integral over the area gives us the area. We have a flat piece of area here. So this is one of those situations. Let me go back to the textbook here, right? This corresponds to number 2, right? The dot product can be expressed as a simple algebraic product EdA, because E and dA are parallel, right? So that's why this is working for that surface. So, and we can fill this out, right? We know what's the area of this, so let's plug back in over here. Well, before we plug in, let's see. Is it going to be any different on the other side for the third surface, the back end cap of our Gaussian cylinder here?
Yes, assuming the other side of the plane is also positive.
Yeah, so the other side of the plane is positive, right? So on the other side is the electric field is still pointing away, right? It's still pointing outwards, but on this side it's pointing away. On the back side it's pointing away. But so is the area vector for the end cap, right? The outward vector for this end cap is also pointing away. So for the third piece, the piece behind the plane of charge in the diagram, the electric field and the area vector are both still parallel. They're both still pointing away from the plane of charge. So we get the same result. E dot dA still becomes E dA magnitude. And that's just going to be E times the area. All right. So the flux through the cylindrical part is 0. The flux through this end cap is just E times the area. And the flux through the back end cap is also just E times the area of the end cap. And we haven't decided yet what the area is, right? We've just drawn a cylinder, but we'll see how that comes in a second. So my total flux, 0 plus EA plus EA is just 2 times the electric field times the area. Right, and remember my total flux is just what I get, right, if I do this integral. So that means from Gauss's law, I can say that 2EA equals the charge inside over epsilon naught. And we can solve, if we solve this for E, the electric field, I see that the electric field is just charge inside over 2A epsilon naught, right? So, but we weren't given, we don't know what the charge inside necessarily is. We don't know what the area is. So we have one more thing we need to do. If we remember the surface charge density here, we can figure out what the charge is inside this. The charge is on the circle that's inside of our surface, right? If you imagine that our imaginary cylinder passing through this charge plane of charge, right? The cross section is a circle, so there's one circle, right? That's this circle here, that's inside our surface, our cylindrical surface. So how much charge is going to be in that circle? What's the Q inside? We can write it in terms of the charge density sigma. Can anybody see what that's going to be?
It's the area divided by the density. Sorry, it's the density divided. No, wait. It's the density multiplied by the area.
That's right. It's the density multiplied by the area, right? So the charge inside is this how many is the charge per surface area, right? This is how many coulombs per square meter times the area, right? And that's always going to be the case, right? The charge inside, if you've got a surface charge, it's just going to be the area times the surface charge density, right? If you look at the units, right, this turns out to be charge because the units of charge density is coulombs per square meter. The units of area is square meter, right? So the units of sigma times A is just coulombs, right? Which is units of charge. So let me replace my Q inside down here with just sigma times A. right? And this is good because our areas, which we haven't really defined, cancel out. So it doesn't matter how big or how small we make our imaginary cylinder, and it shouldn't, right? Our imaginary cylinder shouldn't actually affect the value of the electric field. It doesn't matter how big or how small we make this cylinder because the area cancels out. And what we get is the electric field is just the surface charge density divided by 2 epsilon naught. Right, for the magnitude. And its direction we already know is going to be perpendicularly outwards from the plane of charge. So the most important thing to see about this is how is this electric field depend, and this is something that we didn't know going in, right? How does the electric field depend on how far away from the plane of charge we get? I'm looking at this result. Go ahead.
The strength of the electric field?
Yeah, the magnitude, so the value. How does this result, right, the sigma over 2 epsilon naught, how does that depend on how far away? Or let me put it this way, is there anything in this equation that's, related to d, the distance
No.
from the plane of charge?
Wait, sorry. Density.
Say that again?
Wouldn't it be density?
Well, it does depend on the charge density, right? So if we put more coulombs per square meter on this plane, then we're going to have a bigger electric field, right? So the electric field depends on the charge density. 2 and epsilon naught, those are just
Constants.
right? So those, that doesn't really matter. But so what's going to happen if I measure the electric field, 1 inch away from this plane of charge, and then I measure the electric field 10 inches away from the plane of charge? Is the magnitude any different?
Say that again? Wait, so... yeah, never mind.
Maybe I'm making this sound too complicated. All I'm saying is the electric field here does not depend on the distance you are away from the plane of charge. Right? It doesn't matter how far away from the plane you get, you're still going to have the magnitude sigma over 2 epsilon naught. Right? That's very unlike Coulomb's law, right? In Coulomb's law, when we had a point charge, there was an r squared in the equation, right? So the farther away you get from the point charge, the electric field gets weaker. There's no r in this equation. So if we get farther away, this doesn't that doesn't change the magnitude of the field there. And you can kind of think of it as, well, if it's an infinite plane of charge, right? And you look at it, you see an infinite plane of charge. Even if you get really far away from it, it's still infinite. It's still going to look just as big, just it's infinite. So what we have here is, this is a uniform electric field, because it doesn't change with respect to distance. It's a constant value. And we've already, we've worked with uniform electric fields a little bit already. We've solved some problems involving them, but we haven't seen until this point how we make them or where they come from. Right? But you can make a uniform electric field if you have a infinite plane of charge. And in reality, it doesn't even need to be very infinite, right? In reality, if you have a plane of charge, so some plane that has charge spread out evenly over it, near that plane of charge, you're going to have a uniform electric field. Once you get kind of near the edges, or if it's a finite or a real plane, once you get near the edges or once you get far away, then it is going to change. But near it and not near the edges, you're going to have this uniform field. So this is how we get uniform electric fields, by spreading charge out over a plane. Questions about the first Gauss's law super example.
So for this example, it is basically the opposite of Coulomb's law. Like, distance does not matter necessarily.
Yeah, yeah. I don't know if it's the opposite of Coulomb's law, but it's definitely different.
Well, yeah, the opposite, like, principle.
Right.
Kind of.
Yeah. From a point charge, when you get farther away from the point charge, the electric field gets weaker. For an infinite plane of charge, if you get farther away from it, the electric field doesn't get any weaker. It doesn't change. Right. So the diagram that I'll show you before wrapping up this is also from the book. Right here. Right. If you look at figure 24.14 here. Right. Here's your plane of charge. We're kind of looking end on at it. And then we've got a uniform field coming out from each side of it, right? On one side, it's always pointing away from the plane. It's positive charge. But as you get farther away, right, the electric field lines there are still evenly spaced. So the electric field is still the same magnitude, no matter how far away you get. Other questions on the infinite plane of charge example?